All right, good afternoon, guys. So here is the Unit 8 review key. So number 1, we construct the galvanic cell from metallic silvers and silver nitrate, metallic iron and iron nitrate with potassium nitrate salt bridge. Standard reduction potentials for silver and iron are 0.8 and negative 0.44 volts respectively. Sketch out the cell and do all that crap. So here we got first one, A, sketch out the cell. So we need at least the metal in the nitrate, the metal in the nitrate, the salt bridge, the wire. That's all we need for A. There's other stuff on there because there's other parts to this question. Write out the overall reaction that will take place. So we have to figure out which one of these is being reduced and which one's being oxidized. Because the iron is negative, we're going to have to make that one positive. One of them has to become the other sign, and because 0.8 for silver, if we reverse that, we would have negative 0.8 and negative 0.44. That would not give us a positive E for the cell, so we reverse the iron, and that has positive 0.8, now positive 0.44. So because the silver is being reduced and the iron is being oxidized, we've got the silver going to silver solid and the iron going to iron 2+, and to balance the reaction, we have to balance the charges. So there's B, the balanced reaction. Okay. Label the cathode and the anode. So here on the chart, we got the cathode and the anode because the reduction is taking place at the cathode, and this is actually being reduced, and we got the oxidation taking place at the anode, so the anode is being oxidized. And then, so yeah, cathode, red cat, of course. Then D, indicate precisely where oxidation and reduction are taking place. Precisely they're taking place at the surface of the electrodes. That's where the electrons are available, or where the reaction is taking place, whether it is the iron becoming iron 2+, or where it's the Ag+ becoming Ag solid at the surface of the electrodes themselves. So that is where they're taking place. Draw arrows to indicate the flow of electrons. Electrons flow from the anode, where they're being produced, to the cathode, where they're being consumed. So they're going that way in this case, or if you drew it the other way, then the other way. Indicate which direction the ions are flowing in the salt bridge. So we got the electrons going this way and the negatives continue that way. Or you can see the positives are also going this way to cancel out the negatives that are going this way. So anyway you want to think about it, potassium is going that way, the nitrate's going this way in the salt bridge. Determine E for the cell. So we got the 0.8 plus the 0.44 gives us 1.24 volts. That is GH over time, which electrode would lose mass and which electrode would gain mass. So we have here the one that's being reduced. That one is forming solid from the solution. So that one's going to gain mass. So the silver electrode will gain mass, and the iron will become iron 2+. So the iron electrode is actually losing mass because the solid's turning into solution. I've seen a few questions sometimes that ask which one is the inert electrode, which one doesn't actually take part in the reaction, and that would actually be the silver electrode in this case, because it doesn't really matter what metal you have over here. As long as the metal is in the solution, it will plate onto the surface of that thing. You don't actually need silver on this side. You could use just another piece of iron, or you could use, well, actually not. No, you actually could use iron because you have silver in the solution here. So you could just use a piece of graphite or whatever other metal, copper maybe inside there, because it's just going to plate on the surface of whatever metal is there, because it's the ion that's actually being reduced, not the metal itself. So you'd say that electrode is inert. Even it doesn't take place specifically in the reaction. It's just being plated upon. Anyway, doesn't matter. It's not on this thing anyway. Likelihood of you seeing it on the AP Chem test are pretty small, so it doesn't matter. All right, that would lose. So we got the iron electrode would lose mass, and the Ag electrode would gain mass because the reduction is taking place, so it's gaining the mass. And then we have I, if we started with 0.5 molar of the iron, right? Yeah, iron nitrate, and 1.5 molar of the silver nitrate. Well, standard potential, which we found, the 1.24 volts, would be if they're both at standard state, which means they're at 1 molar each. Well, if we reduce this and we increase this over here, it's going to shift the reaction toward the products, which means that the reaction is going to go faster. The cell is going to go faster, which means that it's going to have a higher potential than the standard potential. So E for the cell would go higher, so it's greater than E standard. And then J, determine delta G for the reaction taking place in the cell. So we use the equation, delta G equals negative NFE, and E is in volts. Now volts, remember, are in joules per coulomb, so that's 1.24 joules per coulomb. Faraday's constant is 96,500 coulombs per mole. I think it's 485, but you only need 3 sig figs here. And then we got the -2, that is the number of electrons, right? 2 electrons in the balanced in the balanced reaction. There's 2 electrons that are transferring from one to the other. So that's where that N comes from, 2. And the 96,500, and that is 1.24. When you multiply all 3 of those together, you get negative 239,320 joules, because the joules are here, and that can be changed into negative 239 kilojoules. You don't have to, but you can. All right, so that is number 1. Number 2, I apply a current of 15 amps to a solution containing solid copper, blah, 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 for 1.15 hours. What mass will be precipitated in this time? This is just a big, long conversion. So we go from hours to minutes and minutes to seconds. Now here we use the amps to go from seconds to coulombs. An amp is a coulomb per second. That is the current that runs through the wire. And then we use Faraday's constant in the next one, which is in coulombs per mole of electrons, but we use the inverse of it because we need the coulombs on the bottom. Then we use the balanced equation for the plating of copper, for the reduction of copper, because it's copper 2+, we need 2 electrons, so 2 moles of electrons for every 1 mole of copper using the balanced equation. And then we use the molar mass of copper. 1 mole of copper is 63.546 grams. So we get 20.447 grams, and we have 3 sig figs, because 3 sig figs in the beginning, and that gives us 20.4 grams. Number 3, what are the names of those 2 complex ions? So the first one, we got cobalt and 5 ammonias and a chloride, and then 2 chloro, and then 2 chlorides over here. So the name of the complex ion, which is just this part right here, is pentaamine. Actually, that should have 2 M's. 1 M is a different thing because we like to confuse you. So it's pentaamine chlorocobalt 3 chloride. So this is the name of the complex ion, and then chloride is just the other part of the ionic compound. So pentaamine, because there's 5 amines, and then just chloro, because there's 1 chlorine attached to the complex ion. And then cobalt 3, how we know it's cobalt 3 is that there's 2 chlorides here, and so that must mean this is a negative 2, which must mean this is a positive 2 in order to cancel out the negative 2. Well, cobalt has to be a 3+ in order to cancel out the 1- and give us a positive 2 total for this whole complex ion, such that it can cancel out the negative 2 there. All right, for B, we got potassium hexacyanoferrate 3. Now, because it forms a negative ion, we have to change the iron's name to ferrate. And we know it's a 3 because there's 3 potassiums giving us a 3+ charge. The charge on this total ion right here must be a 3-. And so there's 6 cyano groups, and each of those is a -1. So when this iron and this -6 add up to -3, this must be a 3+, a positive 3. So that's why the 3 right there. So that is the name of those 2 ions, but again, that won't be on the test tomorrow, so you don't really need to worry about it too much. All right, number 4, a solution has an initial concentration of copper and a concentration of ammonia. What's the concentration of copper at equilibrium? So we start with our 2 concentrations, 0.01 and 1, and none of that, and then we use up all of the copper, essentially all of the copper, which means, because there's a 4 here, we use up 0.04 of that, and that, because there's a 1 and a 1, the same amount of this is made as this is consumed. So we use up essentially all of it, but not quite all of it. That's why we put our X right here, and then we subtract, and we get 0.96, and this is just how much was made, 0.010. So we construct our equilibrium expression. K is equal to the products over the reactants raised to their stoichiometric coefficients. Don't forget those. Don't remember any of this crap for tomorrow. No, please don't forget the stoichiometric coefficients. And then when we solve for X, we get 2.35 times 10 to the -16 molar. Number 5, we got the same type of problem except different numbers, and I'm pretty sure we went through this one in class together. So 1.16 times 10 to the -19 molar. It's the same exact thing. Go over it if you want. This time is a 3 because there's a 3 and whatnot. This is I'm pretty sure we did this one in class. This is a bidentate ligand, so even though iron has a 3+, so it would want 6 ligands around it. This is a bidentate ligand, so essentially it has 2 teeth, and so it can actually do it 2 times. So there's 2 and 2 and 2 in there, like these, and it munches on the iron. And I've been at school for a long time. Okay, anyway, so we got 1.16, but again, we did that in class. All right, number 6 asks us to explain when a few drops of concentrated NH4OH is added to solution of silver nitrate, a white precipitate appears, But when an excess of concentrated NH4OH is added, the white precipitate disappears and the solution is clear and colorless. There's some things here that give you clues as to what's happening. White precipitate, that means a solid appears. There must be some precipitation reaction between the solution of silver nitrate and the NH4OH. But when an excess of concentrated NH4 is added, the white precipitate disappears. Excess, concentrated, and a precipitate disappearing pretty much means you're going to have a complex. Also, this KF means you're going to have a complex, and the fact that a complex is listed right here means you're going to have a complex. You're going to have to use both of these things to figure this out. So, first, the complex forms from the silver and the hydroxide. Silver precipitate forms with the hydroxide. AgOH has a low KSP, which means it will form a precipitate. It is not very soluble. So that's the first part. That's the white precipitate. Now next, anytime NH4OH is in a solution, there's also some NH3, because anytime this is in a solution, you're going to have this equilibrium back and forth. NH4OH in equilibrium with NH3 plus H2O. Because this is a base, or it's a moderate base, the NH4 is also a moderate acid, so it can release one of its hydrogens, and that can form combined with the OH that's there and form H2O. So anytime you have NH4OH in solution, you also have NH3. Now the NH3 forms a complex with the Ag. Even though the AgOH has a very low KSP, it still dissolves a little bit. As the Ag is consumed by the reaction, the Ag plus 2 NH3 reacting to form and in equilibrium with AgNH3 plus, as the reaction occurs, it's using up that Ag solid that is dissolving from the AgOH. And as that is being used up, that drives that dissolving reaction forward more and more and more and more and more until all of the solid is gone. More of the solid AgOH dissolves until none remains. All the solid is gone. So that's number 6. Number 7, I didn't want to use another page, so I did it over here. This one is our adding reactions and multiplying K values together one. So calculate the molar solubility of AgBr in 1 molar NH3 with the KSP of AgBr is 5.0 times 10 to the negative 13. We also need the Kf of AgNH3 because that's the complex that would form, but it's right here already. So we have 2 reactions going on. This one, the dissolving of AgBr solid into Ag plus Br minus. The KSP is 5.0 times 10 to the negative 13. And we have the complex forming Ag plus 2NH3 reacts to form AgNH3 plus. There's 2 ligands because it's a 1 plus charge. So when you add these 2 reactions together, you get AgBr solid plus 2NH3 reacts to form AgNH3 plus Br minus. And when you add 2 reactions together, you have to multiply their KSP values. When you multiply these 2 KSP values, K for this reaction is KSP times Kf, you get 8.5 times 10 to the negative 6. Still negative, but not quite as negative as it was over here, so more of it will dissolve when it's in NH3, because some of it's forming that complex, and that's affecting the solubility. So we set up our equilibrium expression, which is going to be 8.5 times 10 to the negative 6, which is the K value. 8.5 times 10 to the negative 6, which is the K value there, and then that equals x squared, because you have 2 x's over here for the products, over 1.0 times 10 to the negative, 1.0 minus 2x squared, because there's a 2 right here. We don't need this because it's a solid, so it doesn't matter how much is in there. So solids do not appear in our equilibrium expression. So when we solve for x, this value is pretty low, so I probably could have just said that was negligible, and I work it out anyway, and I find that it really was negligible. So we could have just said that was negligible and then just taken the square root of both sides, but I worked it out anyway, and we found that, yes, it's actually just the square root of 8.5 times 10 to the negative 6. So that's 2.9 times 10 to the negative 3. It's not changed enough to actually make it anything other than that. So that 2.9 times 10 to the negative 3 is the solubility of AgBr in 1 molar NH3. Okay. Yeah. Let's see. That's it. Okay.